Okay, welcome back. In this lesson we're going to look at the method of using eigenvalue approach in determining the stability of a dynamical system, usually a 2D system. So if you find your eigenvalues or your characteristic equation and then discover that the first case is 1 if lambda 1 and lambda 2 are both less than 0, so both eigenvalues are real and negative, then the equilibrium point is asymptotically stable, or it's an attractive node or a sink. So if your lambda 1 and lambda 2 are both greater than 0, which means that both eigenvalues are real and positive, this is an unstable repulsive node, which is also known as a source. So if lambda 1 is less than 0 but lambda 2 is greater than 0, they are real and differing in sign. One is negative and the other is positive. We have a saddle point. All saddle points are unstable. So it's an unstable saddle point. So if lambda 1 and lambda 2 are given as a complex number, which means that for alpha is less than 0, so this is the real part of this eigenvalue is less than 0, so the complex conjugate with a negative real part, then it is a stable spiral or a stable focus. If lambda 1, lambda 2, a complex number with alpha greater than 0, then the complex conjugate with a positive real number, then it is unstable spiral or unstable focus. If lambda 1, lambda 2 is equals to plus or minus vi, the complex and purely imaginary, since alpha is equals to 0, then it is a center and it is neutrally stable. Case number 7, not isolated fixed points. So for not isolated fixed point, we have got if eigenvalues are real and equal and repeated. So repeated and equal and negative. If they are repeated, equal and negative, say minus 3 for lambda 1 and lambda 2, then we have a stable node. And if real, equal and positive, we could have unstable node, also known as a degenerate stable or a degenerate unstable. So if they are negative equal, they are called degenerate stable. If they are positive equal real, called degenerate unstable. And last case is interesting. If one of all them are 0, we have an inclusive decision. So if all or one of them are 0, we have an inclusive decision. We need one more condition to establish the stability of the system. So if we've got 0, lambda 1, lambda 2, both of them being 0, it means that they are inconclusive. We cannot conclude. We need to do more tests and more decisions. Right, so let's look at this example. So analyze the stability of equilibrium point for this system. This is the system. So this system can be written in matrix form as x lambda y x prime y prime is equals to 2, 2 minus 1, 2 minus 1, 3 1, 3 1 xy. So the system has an equilibrium point at 0 0. Satisfy that the system have got an equilibrium point at 0 0. I think I've done this in our previous questions. I did this, so we got that 0 0. Or we can try this system and establish that it's a 0 0 equilibrium point. So we have matrix A which is equals to 2, 3 minus 1, 1, and characteristic equation is obtained using a determinant of A minus lambda identity matrix, which is equals to 2 minus lambda, 3 minus 1, 1 minus lambda. So determinant of this times this times this, minus its diagonal, this diagonal, which is 3 times minus 1. So our characteristic equation will be given by lambda squared minus 3 lambda plus 5, which is equals to 0. Solving this, you get this. Simplify this, you will get lambda is equals to 3 over 2 plus or minus the square root of 11 over 4, which is equals to I. So since the real part of this eigenvalue lambda 1 lambda 2 is 3 over 2 and is greater than 0, we conclude that the equilibrium point, this 0 0, is unstable spiral. So it's unstable spiral. So if it's unstable spiral, it can be this or it can be this solution. Alright, so thank you.